Holy experiment. Right, could y'all close the blinds back there so you can see the board gloriously? We're going to go on into chapter 7 today, which is about gravity and planetary motion. Everybody, please keep your mask up above your nose, please. Especially now with all the cases that we've seen in the beginning, we need to really make sure to keep our mask on. Nicholas Copernicus in 1543 described planetary motion. He was in Poland and he proposed the heliocentric theory. Did you hear about this in history class? About Galileo and Copernicus and the Pope and
Not much more before was Copernicus than Galileo.
Galileo was after him. Galileo was in the next century. So about 40 years later or so. Well, who's this? Is that Dominic?
Yeah.
So he described the planets like this, where the sun in the middle, and he wrote in Latin. And he said that the planets, which he knew about Mercury and Venus and Earth, Mars, and then you have, oh my gosh, what, Jupiter, Saturn, and then what would that one be? I can't even read that. Can anybody read that one? I don't think that's Pluto. I don't think they knew about Pluto at the time. I can't read that. I want, maybe that was just a mystery planet which you didn't know the name of yet. No, I don't think they knew about Pluto at the time. Pluto, I think, was a newer discovery. Because it was such a little planet, I don't think they could see it. So I wonder if it was just some mysterious planet he didn't know the name of yet, which could have been Neptune. It could have been Uranus, but I don't think, it's only two it could be. I don't think Pluto they would even know about. It's too small for them to see it. So one thing he was correct about is that the sun is in the middle and the planets go around the sun. That's correct. But he wasn't fully correct about this. Do you know what he was wrong about in this model?
The orbits are perfect circles.
Very good, exactly right. Yeah, we learned yesterday about this. You know, you showed the orbit of Mercury, right? No, Mars. And it was not a perfect circle. There was one part that was bigger. There was a larger path on one side than the other side. What is that called when it's more of an oval shape than a circle? Did you learn in geometry class? Begins with an E. Yeah. Ellipse, very good. So planets move in an ellipse. They don't move in circles. I mean, they could move in circles, but they usually don't. And I'll show you later on, like around the board, I can show you why they don't. But for right now, just know that they don't usually move in circles. There almost always will be an ellipse, where there's a larger part of the orbit and a shorter part of the orbit. So he thought that the planets moved in a circular path, which was not correct. But he was correct. He was the first one to really propose this idea that there is planets around the sun and the sun stays still. So this was the thought before Copernicus, that the Earth is in the middle of the solar system and that the sun moved around with the other planets. That was the prevailing thought before he came along. Because that's what it appeared to be. I mean, people saw the sun move across the sky, and so they assumed the sun had to be moving because that's what they saw happen. But it's just the reverse. The sun was in the middle, not moving. The Earth is moving. And so the stars out here, they thought just stayed in place. And then you have the sphere of the prime mover. I wonder if that's what he was writing out there. I still can't read that, but I wonder if that's more of what he means right there. Is that, I can't, I'll look up later and read it because I can't read it from my computer. But he might have just said that's heaven, basically. Maybe that's what he was saying. So just beyond there is where God reigns with the angels. I'm not sure though. I'll just see if that's what he meant by that one. So they knew about some of the planets at the time, but they didn't know about all of them. Did you get that down?
No.
Do you know which planet you can really see very well, like just without even a telescope? That you can see it with your own eyes? Yeah, that's right. Do you know what it looks like in the sky?
Like a star that doesn't twinkle.
Exactly. Yeah, it's basically a pretty bright star. That's what it looks like in the sky. You can see it especially at dawn and at dusk. It's called the morning star or the evening star because it's usually the first star you can see at dusk, and the last star you see in the morning. So if you look in the sky and if you see really the brightest star, that's actually Venus.
If Mercury is closer, why can't we see that one?
Well, that's a good question. Mercury is not reflective. Venus is. Venus has very, very thick atmosphere, just these clouds. And the clouds are reflected. Have you ever like driven in fog and your headlights like show the fog and it like reflects back into your eyes? You can't really see the road. So fog and clouds can be very reflective. That's why Venus looks so bright because the sun hits the clouds, reflects off, like they're like snow. You know, it snows the same way. It reflects the light back. And so Venus appears bright because of that. Mercury is just a rock. It's not nearly as reflective as the clouds are. And so it doesn't really glow. The other reason why is because the sun is so close to it, it's hard to see Mercury because you have to look at the sun basically to see Mercury. And Mercury is a tiny speck on the sun as far as that's how we see it usually. It's not far enough away from the sun for you to see just Mercury without the sun in front of it.
Is the North Star not the brightest one?
North Star is not that bright. I mean, it is bright, but it's not as bright. What is he doing? It's not as bright as Venus. Venus would be brighter. I mean, North Star is good for navigation, you know, but it's not the brightest star. But it's definitely not a dim star. I mean, you can see it pretty easily in the sky.
Isn't Venus closer to us?
I'm not sure. I would no, actually it would be. All right. So moving on to the next person. So Tycho Brahe in 1560s, so he's about 20 years after Copernicus, Danish astronomer. So he was he built on Copernicus' idea, and he said that the sun and the moon orbit the Earth. So kind of had an in between you know the old theory, which that the Earth is in the middle of the solar system and that planets move around the Earth. He knew that wasn't correct, but he wasn't like Copernicus as far as saying the sun is in the middle, everything goes around it. What he said is that the sun is in the middle, but the sun actually moves and it rotates around the Earth, and that's why we see the sun move. According to him, is that it actually does go around the Earth. But the other planets, he said, they travel around the sun, which was not correct, but it helped explain the paths that you saw with the planets. So they would chart the planets across the sky, and they knew that they had to rotate around the sun based on their paths. But they also couldn't reconcile the idea that the sun actually moved across the sky, and they didn't believe it could just stay still. And so he was compromising those two beliefs and said, the planets do orbit the sun, but the sun also orbits around the Earth. And the moon also orbits the Earth. So he got further away from the right model at this point. Copernicus was much closer to the right model. Johannes Kepler, a little bit later on, 1601, he was in Germany. He worked with Tycho Brahe, and Johannes Kepler used math to explain planetary motion. And based on the math, he came up with the correct model, which is what you see down here. So he realized that the planets do go around the sun, they all go around the sun, and they go in an ellipse. And there's always a part when they're further away from the sun and a part when they're closer to the sun. So based on that, so the Earth goes around like this. Where do you think it would be wintertime for us? Right here when you're far away from the sun, or over here when you're closer to the sun? You think so, right? But that would make sense. But actually, wintertime for us is over here, when we're right here. We're close to the sun, which doesn't really seem to make sense. But what causes the seasons is actually not how close the Earth is to the sun. It's something else. Did you learn about that in Earth science? What makes the seasons change?
Isn't it if the sun's facing like whichever hemisphere?
Yeah, the hemispheres, like basically the Earth tilts, right? And so there's a side that's pointed towards the sun. And so if the north is tilted towards the sun, it's summertime for us. If it's tilted away from the sun, it's wintertime. And so it's the tilt of the Earth that causes the seasons, whether it's pointed towards the sun or away from the sun. So it's not the distance from the sun, it's which way are you tilted.
So then for like people in South America, like when they're close to the sun, there would be summer for them.
That's right. Yeah.
And wouldn't it be like a way hotter summer than?
They do have some, like Australia has very hot summers. And it's, in Antarctica is a lot colder than the North Pole is during the winter time. That's true. But a lot of the South is just ocean. And the ocean water helps keep it getting too hot. So yeah, if they had a lot of land in the South, it would be very, very hot down there. But they don't. And Africa is the biggest landmass. Around the equator, it is quite hot there. But when you get further south, it gets smaller and smaller. And with less land and more water, the temperatures kind of even out. And you don't get extreme temperatures if you're around a lot of water. That's why Florida doesn't get too hot, because you have a lot of water around Florida. Sorry, I just lost my place. Okay, so right here. So you said that the sun is in the middle and that the planets go around. So he, along with Copernicus, had the heliocentric model. And then Galileo, a little bit later, agreed with them and further promulgated this theory that the sun stays still and that planets go around the sun. People were very angry about this at the time. Did you hear in history class about the anger people had about this theory and what they did to Galileo and others who believed in this idea? So Galileo went around town, he was in Italy, and he talked about this. And what did people do? I mean, they got so angry, they called for his arrest, they said they need to shut him down, he can't speak, he can't write books, because they believed he was preaching heresy. They believed the Bible said that the earth is in the middle of the solar system. And they believed he was going against the Bible. And so they were very upset and angered by what he was saying.
Didn't the church initially not go against it, but they said that he couldn't publish it?
That's right. So the church supported Copernicus before Galileo. So the church was always for this theory. The heliocentric theory was supported by the church a century before Galileo came along. So for 100 years, the church had supported, given money to Copernicus, supported his work. So the church understood there's nothing against church teaching about this idea. It was, they knew that, but because the people were getting upset, the church told Galileo, just calm down. Galileo was not always nice about what he was saying. He basically said, if you didn't agree with me, you're stupid. I mean, he just went around town insulting people. And of course, people were really upset because they had their beliefs and he was insulting their beliefs. And so the Pope said, we believe what you're saying, but you need to not be so cocky and not be so, so abrasive to people. You need to state your facts, but not say in a way that makes people feel like that they're stupid for not believing you. But Galileo just went against the Pope and he wrote a book basically making fun of the Pope and saying the Pope was stupid. And so he attacked the church too. And at that point, he was put under house arrest. He could still work. He could still write books. He could still he could still do what he wanted to do, but he just couldn't go out and speak in public to people because he was upsetting people. And he didn't have the facts either to say what he was saying. I mean, he was right about what he was saying, but he didn't have the hard evidence to support his idea either. All right, so Kepler developed 3 laws of planetary motion based on what he saw. And the first one is that the planets go in an ellipse. And so and the ellipse are always like this, where the sun is on one side of the ellipse. The planet would always have one place where it's further away from the sun and a place where it's closer to the sun. An ellipse has 2 foci. Did you learn this in geometry class about the focus of an ellipse? No? So basically what it is that you could have a point from here to here. It's the same distance from here to here as from here to here. So it's these 2 correspond to each other. Basically what you could do to make an ellipse is you could just pull a pin with a string and just go along with the string. And you could create an ellipse that way. But the main thing to know about this really, what he's saying here, is that you have an oval shaped path for the planet. The sun is on the middle, it's at the side. That's the main thing to know about this. Yes, you know this too, that comets orbit around the sun just like ellipses do. Comets can take years, even hundreds of years, to orbit around the sun. A comet, do you know what a comet's made out of? Did you learn about this before?
Yeah, ice and rock.
Yeah, ice, rock, dust. It's basically just a burning block of rock in the sky. And so what you see is the tail is just burning dust, burning smoke off the comet. And the sun melts it and causes it to burn.
So comets never like get thrown from the sun.
Get thrown from the sun?
Like they never get thrown from the sun's gravitational pull.
They can. I mean, some do. We don't know. I mean, we can't really trace everything that's in the universe, but yeah, some definitely could get not thrown out exactly, but just fall out of orbit. And they can either fall into the sun or fall out. That's definitely possible. Those things can happen. But many comets just stay orbiting for centuries. They just orbit around the sun.
How come like we only see comets in the summer?
You don't just. You can see them any time of the year.
Or like that's when they mostly are.
It's the ones that are appearing right now are summertime based, but it's just a coincidence. They can be at any time of the year. It's not just summertime. That they can be at any time.
Or like comets are like shooting stars, right?
They can, yeah, usually, well, they can be meteorites too. So a comet, usually a shooting star is not a comet. Usually what you see as shooting star is a meteorite. It's like a bit of rock or dust that's falling into the atmosphere and burning up in Earth's atmosphere. That's usually what you see as a shooting star. But a comet is different. A comet does not go into Earth's atmosphere. It stays orbiting really far away from the Earth, and it orbits around the sun. And so they're not the same thing exactly. And so you might think of meteorites, maybe, which is just space dust hitting Earth's atmosphere.
Do you know why those are usually in the summertime?
They can be either time of the year too.
But I feel like they're always like in August. Like that's like the peak time for those.
I mean, I'll look up more than see, but I've definitely seen them. I remember seeing them when it was really cold outside too. So I don't think they're just in the summertime. Well, I know they're not because I've seen them before, but I don't know if there'd be more of it, but that would make sense to me. on why that would happen. Because it's just space dust, which can happen any time of the year. So it wouldn't make sense that it'd just be one time of the year, but it's possible in the summertime that we're in a place where there's more rocks and dust that we're hitting. That could be a possibility. Because the Earth always travels around the same place every year. And so it's possible in the summertime we're over here, maybe there's more dust and rocks in that area than the wintertime. That might happen. I'll have to check and see. But that's what causes meteorites and shooting stars usually. It's just space dust that you're hitting. One famous comet, the Hale-Bopp comet. This is 2,400 years to go around once. So this was discovered in 1995 and it was visible in 1997. So this is a huge deal because this is a once in every 2,000 year comet that you could see. So the last time this was visible was before Jesus was born. It's 400 years before he was born. So it was a huge deal when this happened because it's such a long time for it to go around. So the next appearance is going to be in the year 4,387. I remember seeing this as a kid. I think I was 12 years old when this happened. And you could, it looked like that in the sky. You could just, it was perpetual. It was for a long time. You could look at the sky and you'd see this. Did you get that down? Another kind of comet, which is a lot more frequent, is Halley's Comet. 76 years to complete one orbit. And so most people see it once in a lifetime because 76 years is enough for you to see it once in your lifetime. And you can see how it looks. This is orbit right here, and Earth is down here. So it last appeared in 1986, and it'll appear again in 2061. So it's not often that we really see a comet in the sky that's really visible, but so there are only a handful of them that we can see that are visible to us. Most that we see in the sky is meteorites and not comets. So Mark Twain, he's a famous writer. He wrote Huckleberry Finn, Tom Sawyer. He wrote this. He said that it came with Halley's Comet in 1835. It's coming again next year, 1910. I expect to go out with it the same way that I came in. It'll be a great disappointment in my life if I don't go out with Halley's Comet. The Almighty has said, no doubt, there are these two great unaccountable freaks. They came in together, they'll go out the same way. And he died watching the comet. He had a heart attack. And so the next year, he saw the comet and at its brightest point, that's when he died. So it really is amazing that he just knew that that's when he was going to die. That he was born with the comet, and when the comet came back, he passed away. So some comets have a long period where they take about 200 years to pass, or greater. Like we talked about, the Hale-Bopp comet takes 2,400 years to pass. Others have a short period, like Halley's Comet we just talked about, 74 years to pass through once. So planets have areas where they're faster and closer to the sun, and areas where they're further away from the sun, they move slower. So when a planet approaches the sun on this side, it has to move faster to maintain its distance from the sun because there's greater attraction, greater force, gravity pulling the planet more strongly over here than over here. And so it has to move faster in response to that greater force it's feeling. Kepler's second law says that an imaginary line from the sun to a planet sweeps out equal areas and equal time intervals. I'll go through what this means in a second, but for now, just write this down. So imaginary line from the sun to the planet sweeps out equal areas and equal time intervals. So we can look at, so this is the month, this is month 1, January to month 2, February. And so this would take, and I think there's all just gonna be 30-day increments just to be easier. So from here to here, we'll say it's 30 days, from 1 to 2. 2 to 3 is 30 days. So it's the same time interval from 1 to 2 as from 2 to 3. Take an imaginary line from the planet to the sun right here, and a line from here to here. Get the area of this triangle right here. It will equal the area of this triangle right here. So if you look at the same time interval that the planet takes to go from, say here to here, and the same time to go from here to here, make a triangle. That area you make the triangle is equal to the area that you see right here as well. Does that make sense? Everybody clear on that one? So that's Kepler's second law, that if you look at the same time interval that the planet takes, from here to here is 30 days. From here to here, it's 30 days. Connect the lines from the planet to the sun. The area right here is the same as the area right here.
How is the time the same if the distance are so much greater?
So it would be moving faster. So that's a good thing to point out. That from here to here, it covers more distance, right? Than from here to here. From here, because it's going faster, it can cover more distance in the same amount of time. And out here, it's the slowest, and so it covers a short amount of distance. Becky?
Is that why the days get shorter?
Oh, that's a good question. It has to do more with the tilt of the Earth again. That's more of why we see that. If it's tilted towards or away from the sun, that's more of why we get a shorter, longer day. Because tilted away from the sun, it's going to be a shorter day. On here, you don't have to worry about writing down all these, just write down Kepler's third law in the equation, but don't write down all of these words right here. But I'll explain this on the board in a second. Just the equation. That's Kepler's third law. So capital T represents the period, which is the time it takes to go around the sun once. R is the orbital radius of a planet to the sun. So we can use Kepler's third law to determine the time to go around the sun once for a planet, or its orbital radius, how far away it is from the sun. And I'll explain the board how to do this problem. So for now, just write this down and I'll go through an example with this. Okay, everybody have that down?
What is R equal to?
That's the orbital radius. It's how far away a planet is from the sun. Yes, Lydia.
What is T?
Oh, T is the period. It's how long it takes to go around the sun once. Turn the lights back on. I'll go through a few problems with you. Okay, so in your book on page 174. Let's go through example problem number 1.
What page is that?
174. So the problem that we're looking at on page 174 is Galileo to measure the orbital sizes of Jupiter's moons using the diameter of Jupiter as a unit of measure. He found that Io, the closest moon to Jupiter, had a period of 1.8 days and was 4.2 units from the center of Jupiter. Callisto, the fourth moon from Jupiter, had a period of 16.7 days. So we're going to use that information to calculate Callisto's distance from Jupiter. So I'll write on the board what we know about. So we have Jupiter in the middle and Jupiter's moons orbiting around. You have Io, then you have Callisto further away. And it tells you that Io is 4.2 units from the center of Jupiter. So from Io center to Jupiter center, that's 4.2 units. That's what R equals. R is the orbital radius. It's the distance from the planet center to either the sun center. In this case, it's orbiting around Jupiter, so it's Jupiter center. And it says that the period is 1.8 days. And so it takes 1.8 days for Io to go around the Jupiter once. So that's T of Io. That's the period it takes to go around. And then for Callisto, the period is 16.7 days. So that's how long it takes to go around Jupiter. And we want to find the orbital radius, the distance from Callisto to Jupiter center. So we'll use Galileo's third or Kepler's third law to do this. So it says TA over TB squared equals RA over RB squared. Or sorry, cubed. So A would be planet A, B is planet B, or moon A and moon B. Doesn't matter which one we do for A or B, as long as we're consistent. So if we have Io right here, and Callisto right here and right here, or you have the other way around, we have Callisto for these two and Io for these two, either way, it's going to work out the same way. So we'll just say it like this, where we have the period of Io over the period of Callisto squared equals orbital radius of Io cubed over orbital radius of Callisto. But again, you could have reversed these and done Callisto over Io in both places. Doesn't matter. You with me so far on this? So all you need to do is just plug in what we've been given and solve for the unknown. So we know the period of Callisto, 16.7 days, that goes in for TI. No, as long as you're consistent, as long as you know, in this case, we put IO on the top on both of these. So as long as we keep on doing that, and Callisto on the bottom for both, that's fine. Okay, so the period of IO, 1.8 days. We have the period of Callisto, 16.7 days. And that's squared. And that equals orbital radius of Io, which is 4.2 units over the orbital radius of Callisto, which we don't know. So that's our equation. Did you learn about how you can solve with a cubed variable? Did you learn about how you take the cube root of both sides? Basically, you have to undo the cube first before you do anything else. So to get out this variable right here, to isolate it, you can't divide it as it is or multiply as it is. You need to first cube both sides, or find the cube root of both sides. So you need to raise this to the 1/3 power on both sides of the equation in order to get rid of the cube. Is that familiar to you all from pre-calc? No? Well, do you know what happens when you raise this exponent to an exponent? That they multiply? Did you all learn that before? So when you raise this 3rd power to the 1/3 power, you're just multiplying 3 times 1/3. What does that equal when you do that? Right, so that would just get rid of that side. And so now we just have 4.2 over RC. How about on this side? Yeah, 2/3 power. So now we have on this side, it's all raised to the 2/3 power. You with me so far on that? On how you do that? So now we can isolate RC. So we can cross multiply. But in order to do that, be careful, because these are both raised to the 2/3 power. So what we could do is just separate it out and do this and say that this is raised to the 2/3 power and this is raised to the 2/3 power. At this point now we can cross multiply and solve for RC. Do you all know how to put it in the 2/3 power in your calculator? No? So what you can do, there's a few ways you could do this, but some of you have this feature where you would put in the number 1.8, right in the caret button, and just do 2 divided by 3 in parentheses. Others have an exponent button. You can use the exponent button too. But for right now, if you don't know how to do it, go ahead and take some time to check to make sure you can do this, because in your homework you need to do this. So check right now to make sure you do know how to put in exponents like this into your calculator. Yeah. I don't know if I have that. I can check really fast on my calculator to see what that should be. Let me see. So yeah, you should get 1.47, 1.48. So if you did it correctly, 1.48, 1.47 should be your answer for that one. Everybody good in that? You want to do that? So let's go and write that in. So 1.8 raised to 2/3 power is 1.48 when you round it to sig figs. That's going to be times RC. On this side, we can go and multiply that out too. 16.7 raised to 2/3 power. So that should be 6.5. Did y'all get that? 6.5 times 4.2. 27.4, right? Okay. 27.4. And now we can divide both sides by 1.48 to get RC by itself. When we do that, we should get, what would you all get for that? Yeah. 18.5. Yeah. So that's orbital radius. That's how far away Callisto is from Jupiter. 18.5 units away. Or 18 point, I guess that's how you round it, 18.3, 18.4, 18.5, somewhere around that. That's what you should get for your answer. With sig figs though, actually, we only have 2 sig figs here, so it should run a 19 at the end. So with 2 sig figs, we're gonna actually have 19 for our final answer. So that's Kepler's third law and how you use it. Anything that you want me to go over before we do homework today? Okay, for today, just do number 1 on page 174. Just do number 1 today before you end class. Yes. Let's see. You could use either of them. It wouldn't matter actually, because now you know both information. You know both radius and period for both of the moons. You could use either one.
Fine, thank you. Whenever you want to, you can go to the chapel for prayers. Homework is just number 1 tonight.